you everyone for coming. Of course, I want to thank my fellow co-organizers who did most of the work for leading up to this, and hope everyone has been enjoying it. I mean, I've enjoyed all the lectures tremendously so far, and I'd also like to kind of thank the staff at ICTS who have put in a lot of work to kind of make everything work behind the scenes. Everything has been so smooth so far. And of course, I want to thank everyone for coming here. I mean, some people have flown a long way, so hopefully people are getting something out of this conference. So okay, so today I'm giving two lectures, one today and one tomorrow, and I have this kind of cute title where it's minimal surfaces with and without Higgs bundles. So kind of today I'll talk about one of the cases that Franz alluded to, where you have a Higgs bundle. So these will be minimal surfaces in non-compact symmetric spaces. And then tomorrow it will be without Higgs bundles, which will be more compact symmetric spaces. So the symmetric space that we care about for today will be, well, the lead group will be SL3R. So the symmetric space that we saw with that Mike mentioned was SL3R mod SO3, where these will be unit volume Euclidean metrics on R3. So that's kind of where we're headed. So okay, so just some introduction. Usually things like this get mentioned earlier on, especially in a higher Teichmüller theory conference. But since this is not one, then I had to define Teichmüller space, where we kind of saw aspects of this in Ulrich's talk when he talked about constraint Wilmore being allowed to vary within a conformal class. So the setup is as follows. So we start with S, just a closed surface. I'm genus G at least 2. Okay. And then I could define Teichmüller space as follows. Of course, there's a lot of, I see experts in Teichmüller theory, so they can take an early lunch or take a nap. So kind of the first definition I'll give is complex structures on my surface. So right now, S is just a smooth surface, okay? So with some topology, okay, no additional assumptions. So, but of course I can endow this with a complex structure on S, okay, also known as a Riemann surface. And well, I need some identification, right? Just like with surfaces, if I draw a surface here, that's a surface of genus 2. Here's another surface of genus 2. You don't want to regard them as different surfaces, right? Clearly, these are homeomorphic. So I need some sort of identification. So if I have two Riemann surfaces, the natural thing I could do is identify them if there's a biholomorphism between the two. I certainly need that. Now, if I just stop here, then I have the classical definition of moduli space, from an algebraic geometric perspective, the moduli space of curves. So if I want Teichmüller space, I need one additional assumption with my biholomorphism. I want this as a smooth map that it's isotopic to the identity. And so I don't want my biholomorphism to start twisting things around. Okay, so that's my first definition of Teichmüller space. Now, of course, complex structures in dimension 2, real dimension 2, are the same thing as conformal structures. I have a notion of angle given by my J, rotation counterclockwise by 90 degrees. And this gives me, in turn, a conformal class of metrics. And we know from the uniformization theorem that in each conformal class, since my genus is at least 2, then I could pick out a unique metric of constant curvature -1. So these are just the hyperbolic metrics. Yes. And again, I have the same, I need to identify different hyperbolic metrics. If I just kind of wiggle something around, then maybe that's not good enough. So I don't want those to be regarded as distinct elements. So I look at these hyperbolic metrics up to isometry. And again, the isometry should be isotopic to the identity. So that's the second perspective of Teichmüller space. Now, we see that if I have a hyperbolic metric on S, well, its universal cover, it can be identified with the upper half plane, which I take the disk model. And from maybe first year topology that I can look at a fundamental domain. So here, okay, genus 2 surface, so I should have 8 sides here. 8, okay. And well, the isometry group, let's say the orientation preserving isometry group, H2, well, this is just PSL2R, which we have seen. And so if I have a representation, that is to say, I look at representations of the fundamental group of the surface into PSL2R, what I can do is I can take H2 and I can take the quotient by this representation, and this will descend down to a closed surface here. Now, of course, I need some conditions. I can't just take any representation. And by representation, I mean a group homomorphism from the fundamental group of the surface to this group PSL2R here. There are, of course, some conditions. I clearly just can't take the identity map, right? This is no good. So I need the 2 conditions are that it's a discrete map or a discrete homomorphism and that it's faithful. So that is to say injective. And if I have these 2 conditions, these are often called Fuchsian representations. Then I could take the quotient of H2 by this representation, and this will descend down to a closed surface of genus G, exactly the same topology that I started with. Okay? And if you work this out, then the natural condition that you have on these representations is that it's up to conjugation. So now we see that we have 3 different perspectives on Teichmuller space, and let me just kind of point out that these 3 different perspectives highlight different aspects of Teichmuller space. So here, if you're dealing with Riemann surfaces, this is a holomorphic perspective. Then color chalk here. Green probably doesn't show up very well. Do orange. There was a blue somewhere, maybe all the way down here. Okay, so that's kind of the first perspective. Then the second one, if you're dealing with hyperbolic metrics, this is more differential geometry. This is differential geometric. You're actually talking about Riemannian metrics here. And finally, here, if you're just looking at surface group representations, well, this is algebraic, right? Because you're algebraic and maybe topological, because well, the topology is encoded in the fundamental group of the surface, but then you're looking at just group homomorphisms. So that's an algebraic object. So these are these 3 different perspectives of Teichmuller space. And probably the most important thing I should point out with this is that Teichmuller space is topologically trivial. So it's just an open ball of dimension 6G minus 6. Okay, so let me point this out. It's an open ball. So that's kind of these 3 different perspectives. Okay, so the perspective I'll use today is the second one here from the point of view of hyperbolic metrics. So what you can do with hyperbolic metrics, and this goes back to Thurston, is that you can start to look at degeneration of hyperbolic metrics. Okay, so you can start to ask, well, what does a degenerate hyperbolic metric really look like? In order to do this, you first need the following. You need some sort of topology to put on Teichmuller space to make sense of what does it mean for a hyperbolic metric to degenerate. And this is where we used what's called the Mark length spectrum. So this is if I have a Riemannian metric, so let's say if G is a Riemannian metric, and then if I say script C of S, remember I'm using the same topological surface here, let's say these are isotopy classes of closed curves, then I could introduce what's called the Mark length spectrum, which is just the following pair of objects. So the first component of this pair will be the actual isotopy class of the curve. So this lives in script C of S. And then the second one is I'll record the length of the geodesic in this free homotopy class. So in this case, maybe I want G to be negative. So here, the second thing I'll record is the length of the geodesic. It's the length of the geodesic in the free homotopy class So this is a curve, and this is a number. But I just don't want, I want these pair of objects to run across all of script CFS. And this is what's called the marked length spectrum, because it's exactly what its name suggests. I have a negatively curved Ramanujan metric. I say, let me just kind of draw a cartoon picture. But what I'm saying is that, well, I have this curve here. I have some metric. And I say, well, this curve, let's say this is the geodesic with respect to this background metric. This has length 7, let's say. Okay? And then you go over here. You have this curve here, different homotopy class. You say, well, the geodesic in this free homotopy class is length 23, and so on. And you do it for all the curves in script CFS. So this is, of course, in contrast with the unmarked length spectrum, where I don't tell you which curve it is, but I just say there is a curve of length 7, there is a curve of length 23. So you can see this is some coarse data. But it turns out that Thurston showed that when it comes to hyperbolic metrics, this is good enough to nail down all the information. What do I mean by that? If I define this map script L, which goes from Teichmüller space to this space of marked length spectrum space, which I could see that it's non-negative real numbers. Now you might say, okay, why don't I use positive numbers? But well, we'll see why very shortly. And of course, it's indexed by the isotopy classes of closed curves. Then I could define the following map. I take a hyperbolic metric, which I use H, okay? And I could send H to this marked length spectrum. Okay, so this here, I've indexed script CFS accordingly, and I've assigned a number to each element here. Well, it turns out this map is injective. Which means that once I know the length spectrum of my hyperbolic metric, I've nailed down exactly which hyperbolic metric. And this is rather surprising because, again, if you think about what a hyperbolic metric is, it's a Ramanujan metric. So you have this infinitesimal data of the inner product, and this is all captured by this very coarse data of saying this red curve has length 23, this yellow curve has length 7, and so on. I mean, of course, this is a countable set. It's an infinite set. So there's a lot of information, but this is still coarse. I mean, it's not capturing the infinitesimal data of a Ramanujan metric over here. Okay, so that's kind of the first part. Okay, what I can do is I can now projectivize this space here. So of course I have less than or greater than or equal to 0. So what I can do is I can remove the element that's just all zeros. Okay, so let's write it like this. Okay, so this is the 0 element here. And then I can projectivize. So then we can look at okay, so these are these marked length spectra up to scale. What do I mean by that? I mean, I have a curve here and I have a number here. So if all the numbers here, I can multiply by 2, well, that's the same object in this projective space. Okay, so that's the space here. Okay, so what Thurston furthermore showed, okay, so then if I have this and I have a natural map, then I use pi again, which takes me from this current, or this length spectrum space here, minus the 0 element into this projectivized length spectrum space. If I do that, then it turns out that the composition of pi with L, so this takes me from Teichmüller space to this projectivized space. This too is injective. Okay, so what this means is that if I tell you I have a hyperbolic metric whose length spectrum, this curve is length 7, this curve is length 23, and so on, and then I say, oh, I have a second hyperbolic metric, well, this yellow curve is length 14, and this red curve is length 46, et cetera, well, this can't happen, because then I would have 2 hyperbolic metrics, and one would be twice the length spectrum of the other, and this can't happen with hyperbolic metrics. Okay, so that's additional information about hyperbolic metrics. Okay, good. Okay, I mean, this will come into play later, but it turns out that if you go back to this here, if you just look at negatively curved Riemannian metrics, just the length spectrum, it turns out that if you replace Teichmuller space with the space of negatively curved Riemannian metrics, then O'Toole and Croak have proven that this map is also injective. So if you're just interested in negatively curved Riemannian metrics on a surface, then this coarse data is good enough to nail down the metric. And of course, it's up to isometry. So that's good. Okay, so now using this, I can start degenerating hyperbolic metrics. So let's take a look at that. Okay, there's this famous quote due to Royden. He always says there's two ways to leave all compact sets in Teichmuller space. You can imagine a surface. You could strangle the surface, or you could wring its neck. So it's either pinching or twisting. So let's kind of look at a toy model then. Okay, so if I have a sequence of hyperbolic metrics, here I have again a genus 2 surface, what I can do is I could start to pinch a curve. So let's kind of imagine this separating curve in the middle here. And let's imagine I have a sequence of hyperbolic metrics. So let me say HT here. Okay. And I let this curve, let's say it has length epsilon, and I send this to 0. So what I'm doing is I'm pinching this neck of this hyperbolic metric. Okay. Well, the Collar lemma then shows that if I take maybe an arc that runs transverse to it here, then this arc, this maybe geodesic arc, is comparable to log 1 over epsilon. So what it's saying is that if this red curve goes to 0, then the length of this blue arc goes to infinity. Okay? And on the other hand, curves that are kind of far away from the action, far away from these red curves, they stay moderate length. So maybe I should pick different numbers now. So maybe let's say this is 13 and this is 29. Okay? So you could see that kind of the orange and green curve, they stay away from this red curve. So if I'm just pinching here, not much changes over here. So what this means, combining this last fact about being able to freely scale my length spectrum without losing any information about the hyperbolic metric, means I could just scale everything by a large number. So in particular, if I want something finite in the limit, you'll notice that if I don't do anything, I'm in trouble because this blue arc is blowing up to infinity. Right? So I really can't take a limit. This is going to infinity. So what I can do is I can say, well, this curve is going to infinity. So what I can do is I could rescale and divide everything by log 1 over epsilon. So what I can do is, let's say, divide the lengths of all curves by log 1 over epsilon and hope I get something finite. Okay, so you could start to see what happens. So in this case then, if I do that, well, this red curve goes to 0 even faster. That's okay. There's no problem there. So but now this blue arc is normalized to be 1. Right? So divided by log 1 over epsilon. Okay. And then you can see these moderate length curves. Well, I mean, they might grow a little bit. Maybe if I start pinching, it's no longer 13. Maybe, I don't know, it's like 15 or something. But you can see that if I divide by log 1 over epsilon, this goes to 0. Okay, so this orange curve goes to 0. And likewise, this green curve, maybe it becomes 56 or something. But the point is that it does not grow as quickly as this blue arc here. So when I divide by log 1 over epsilon, this too also goes to 0. So in the limit, I get the following topological object. You can see that all the information is just recorded by that pink curve. And that's where all the interesting action happens. So in the limit, what I get is the following. So in the limit, just this red curve here, because that's all I care about. And the point is that limits of lengths, limits of rescaled lengths are predicted by intersection number Okay, so what do I mean by that? Once again, if I have this orange curve, you see that this orange curve has zero intersection number with the red curve. They don't meet. I mean, you could try to wiggle them in the free homotopy class. You could try to minimize intersection. You see that's zero. And that agrees with a heuristic, because when I rescaled everything, this orange curve wasn't blowing up very quickly. So when I divided by log 1 over epsilon, this was zero. So you can see this has length 0. The same argument goes over here. I mean, the screen curve here. Now this has length 0. But you can see blue, there's something interesting here. Now, of course, I picked a separating curve red here, but if I upgraded blue to an actual curve and not just an arc, you see that the intersection number of blue and red is 2. Right? And you could see that with my kind of approximation, well, this arc was grew like log 1 over epsilon, so when divided by log 1 over epsilon is 1. I pick up some small amount when I go around here, but that's, this doesn't matter. It's some small error term. And then I go behind the surface again, and that's another log 1 over epsilon, which I divide by log 1 over epsilon. And then there's some small amount here to close up. So you can see that when I do that, that's approximately 2, and in the limit, I get 2. You see that that's exactly an intersection number. Okay. Now, of course, this is kind of a simple example of a degeneration of hyperbolic metrics where it's just kind of pinched. But of course, they do more interesting things, pinch, twisted, so on. And what Thurston showed is that all these limits are classified by what are known as measured laminations, which I don't define precisely, but I can draw a picture. So measured laminations. I mean, they are they are related to kind of the foliation pictures that we saw in Mike's lecture. But I won't explain too much about what these are. So what they are is I have a closed set of geodesics. And the order of the words matter because the geodesics themselves need not be closed. The set itself is closed, okay? With some transverse measure. I mean, the transverse measure is invariant under something, but I won't emphasize that aspect too much. Okay, so kind of the trick with drawing these so certainly, the single red curve is an example, right? A single closed geodesic itself as a set is closed. But I can have a bunch of geodesics that just kind of wander around the surface. And, disjoint, closed set of disjoint geodesics. Okay, so I have these kind of curves that wander all around the surface. These are geodesics. Some of them might close up, but typically your geodesic will just kind of wander everywhere around and wander around many times. And you kind of see this picture that they'll kind of bunch up together, and typically the cross sections will be Cantor sets, either isolated leaves or Cantor sets. They kind of look like this. And so on. Kind of, as I said, the trick is to try to draw one side of it only. You can see that. You might get in trouble if I try to draw what's going on the other side, but you can see that they just kind of spiral around. Okay? So these are the limiting objects, and the point is that you can still make sense of intersection number. So I could still take a curve, and I have an intersection. Okay? And this number is what we get when we take this sequence of marked length spectra. Okay, so that's kind of 1970s. So let's move on to SL3R as promised in the title. And of course, minimal surfaces will show up. So I mean, you could already see that in this PSL2R case, I mean, you really don't have a hope of minimal surface. I mean, you have harmonic maps, of course, from Riemann surfaces to H2, but there's no codimension, so you really can't make sense of minimal surfaces. So you need some larger dimensional ambient space. So that's one reason why we move up to SL3R. Okay? I mean, what I'm saying is that it makes no sense to say the words minimal surfaces in H2. Okay? I mean, there's no codimension. But when I say minimal surfaces in the symmetric space of SL3R, then we're in business. Okay, so now let's move to SL3R. And the story starts with Hitchin, the seminal paper Lie groups in Teichmüller space. And what we can do is that you can take PSL2R and stick this inside PSL3R. Okay, so I need to make an important remark. The important remark is that PSL3R, by the way, is the same thing as SL3R. So I taught linear algebra with wonderful reviews last semester or last year, and of course, you teach students determinants and so on. So in SL3R, minus the identities not in SL3R. Okay, so PSL3R is the same thing as SL3R. And let me call this iota then. And there's a naive way, of course, to stick PSL2R into PSL3R, and that's not the map I use. So I want this irreducible map. And it turns out that up to conjugation, there's only one such irreducible map, and it's very explicit. So let me tell you how explicit it is, and if you're bored, you can play around with this to show that actually it is a well-defined map. So, of course, PSL2R acts on pairs, right? So I can look at variables x and y. PSL2R will act on. So if I have A, B, C, D, right? I mean, the determinant condition. So A, B, C, D are real numbers. The determinant is plus or minus 1. Well, then I can act on x and y. Of course, this is just ax plus by cx plus dy, okay? But SL3R also acts on a space, namely homogeneous polynomials of degree 2, of 2 variables. So SL3R acts on homogeneous polynomials of degree 2 in 2 variables. Okay, so I could pick a basis for this. So of course, I have x squared, xy, y squared. And you can see that SL3R will act on this. So if I take this action of PSL2R on these 2 variables, this induces an action on, I guess I should say, this is like sim 2R3. So these homogeneous polynomials of degree 2 in 2 variables. So then PSL2R will act on this. So in this way, you get an embedding of PSL2R into SL3R. Okay, so that's the map that we will use. And consequently, now I have a way to stick Teichmüller space into some larger space. So you remember this third aspect of Teichmüller space that we saw, namely as surface group representations into PSL2R. Well, now I can compose by iota. So maybe capital iota then. And this is a map which takes me from Teichmüller space to some larger space, which I maybe write once as this space of representations. So maybe I get in trouble because it's not quite just up to conjugation, but okay. So I look at surface group representations to now SL3R up to conjugation. And the map is exactly as I described before. If I take a representation for a corresponding Teichmüller space, this was sending me from, so let me just write it like this. It's iota composed with rho. So I have a fundamental group of the surface. This goes to PSL2R, but now I post-compose by iota, and that lands me in SL3R. Okay, so in this way, I can take Teichmüller space, which was this ball, and stick it into this space here. Okay? And now, of course, Teichmüller space is connected. So the image of this, so where I compose to a Teichmüller space lands, it lands in some component. That component is called the SL3R Hitchin component. So this is kind of one of the first instances of studied in this higher rank Teichmüller theory. You can see that the rank of SL3R is 2 as opposed to 1 for SL2R. So again, more representations. So in fact, what Hitchin showed is that this component, which we will write as HIT3. So this is the SL3R Hitching component. This is topologically trivial. It's an open ball again, but of larger dimension. Let me write it like this: 2g minus 2. And then I take n squared minus 1. So in this case, n is 3. So let me write it 3 squared minus 1. So in general, you can define Hitching components for, instead of 3, you have n. It's the same argument here, and you just replace degree 2 with n minus 1. Still 2 variables. Okay, but okay. So let me do this. So what is this? This is 8. So this is 16g minus 16. So it's much larger than Teichmüller space. So Teichmüller space somehow sits inside this Hitching component with a much larger, a very large codimension. Okay, so that's all nice, but you might ask, well, so what? I mean, this is kind of the algebraic perspective, and we're all geometers and topologists here. So why do we care about this? Well, we saw from Mike's lecture, there was this notion of convex real projective structures. Which I just very quickly remind you, well, much in the same way that we saw Riemann surfaces, you have charts to complex plane transition maps or biholomorphisms, real projective structures, you have charts, so this is on a surface, okay? You have charts to RP2, and then the transition maps are Mobius transformation. You could think of this, these are elements of SL3R, and what theorem of Choi and Goldman. And this came out pretty much the same year as Hitching. So this was like 89. 89 or 90. I mean. Okay, so what they show is that the holonomy. You see, I mean, because what I could do with the surface, I mean, this is kind of, Mike alluded to this, and I think many other people will start talking about this in later lectures. What I could do is I could start to kind of take a coordinate patch. This lands me in RP2. And I could try to unfurl, I mean, just develop the image. So I take another open set that overlaps, right? And I do this. And let's say I go around in a loop, right? Eventually I come back. Well, upstairs, I don't come around in a loop. I end up somewhere over here. And then there's a element of SL3R that will take me from this overlap here. So eventually I come back over here, which takes me from this overlap to this overlap. And that's precisely the holonomy map. It assigns to every loop an element of SL3R. So the holonomy of these complex convex real projective structures are precisely the SL3R Hitchin representations. So in this sense, these algebraic objects have geometric meaning. And by geometry, I really mean in terms of GX structure. You have a group acting on some homogeneous space. So SL3R Hitchin representations are useful. Okay, so from these convex real projective structures, what I can also get, again, it depends on what type of geometer you are. I mean, we care about minimal surfaces. So that, if I say this GX structure, you say, okay, that's nice, that's some sort of geometry, but where's my surface? I mean, I want some surface in some ambient space. So what I can do next is we pass to affine spheres, and I really feel like Mike, like a horde of locusts, has just cleaned this field, and there's a couple of scraps that I pick up and present. Okay, so we have affine spheres that we saw yesterday and the day before from Mike's lecture. And what we do is we'll do affine spheres in R3 again. Okay, so I have some convex surface in R3 with an affine invariant transverse vector field. Eta. It's exactly what Mike said. I mean, in Euclidean geometry, you have notions of lengths and angles. Affine differential geometry doesn't care for that because it doesn't preserve that. So instead, we preserve the property of being transverse. Okay, so parallel and transverse, these aspects get preserved. And Mike gave us a geometric explanation of this called the affine normal, which I won't write again, but you could see that if I take my convex surface, I take a tangent plane, I kind of locally foliate it by parallel copies of this plane. Each time I take one of these parallel planes, I get some region that gets cut out. I look at the centroid, I connect the dots of the centroid, and I take the tangent space at the point on the surface. This gives me an affine normal. Okay. In particular, these come in three different flavors, which I very quickly mentioned, since this is something new for maybe most people, which was not mentioned by Mike. So the ones that we care about today are the hyperbolic affine spheres. So here, eta points outside the surface. Okay, now, of course, I forgot a very important comment for affine spheres. So it's not just any surface with affine invariant transverse vector field. I need these points to all point towards a single distinguished point, pointing to a distinguished point, so that I actually get a sphere. And where that point lands gives me my three types of affine spheres. So we saw from Mike's lecture, the hyperbolic ones are the ones that that point outside the surface. Now, again, I have a notion of convex, so inside and outside makes sense. Then I have the elliptic affine spheres, where eta points inside. And then the final ones are the parabolic ones. And this one, eta is parallel, so it points towards infinity. Okay, so we will focus on these today. These are also very interesting from the perspective of geometry. So the elliptic affine, okay, so before I make additional comments, let me just give you some examples so that we know what we're talking about. So of course, for the hyperbolic affine spheres, I don't, I mean, we saw that kind of the canonical example of a hyperbolic affine sphere in R3 was one sheet of the two-sheeted hyperboloid. And we saw that minus the position vector, of course I could translate it, minus the position vector was precisely this affine normal. And the distinguished point was the origin. So let me just kind of repeat this picture that we saw. So here's the hyperbolic affine sphere. Now for the elliptic affine spheres, it's probably a very natural affine sphere to study, and maybe the first example one should see when dealing with affine spheres. So example for the elliptic ones, it's the ellipsoid. So if I have an ellipsoid in R3, that's an example of an elliptic affine sphere. Now you see that if I take the Euclidean normal, they won't all point to the center. But if I kind of stretch things accordingly with the ellipsoid, then you can see that the affine normal precisely points towards the origin. And of course, I can always translate my affine sphere. So I can make this distinguished point, the origin. And this last one, parabolic ones, since we won't see them today, maybe I will mention without drawing or writing that the elliptic paraboloid will be an example. So these are the three flavors there. Okay. Right. Okay. Time permitting today, I'll point out one instance where these elliptic affine spheres will appear. Yes. Oh, yeah, of course. Yes. Yes. Well, the theorem of Choi and Goldman. Oh, okay. I was being very sloppy. So if I have a convex real projective structure, I have a holonomy map. Okay? That's a representation into SL3R. You might ask, what is that representation? So the theorem of Choi and Goldman is telling you it's exactly the Hitchin component. So that all these algebraic objects, surface group representation into SL3R that are Hitchin, that means a deformation of a Fuchsian representation. Well, these arise from these natural geometric objects. this will not be a crucial theorem to kind of the results I hope to get to very, very shortly in terms of minimal surface, but it's needed to kind of set things up. Okay. Nor are hyperbolic affine spheres really that crucial to, I mean, they're important objects, but it's kind of one step towards where I'm trying to go, namely minimal surfaces in the SL3R symmetric space. Okay, so then there's this analytic theorem of Cheng and Yao that was kind of alluded to by Mike without explicitly referencing this result. I mean, it's a strong result. So what do they say? It says that any hyperbolic affine sphere, I mean, maybe I need equivariant affine sphere, is the positive cone. So let me just state it, I mean, we're only dealing with affine spheres in R3. Of course, you could deal with affine spheres in a higher dimension, but for today's lectures, only surfaces in R3. So any hyperbolic affine sphere is is asymptotic to a positive cone over a convex set, non-empty, proper convex set in R2. So it's the picture that we saw yesterday. I could also say, RP2. If I restrict to an affine patch, then maybe my picture looks like this here. There's my copy of R2. I take a look at its positive cone. So of course, cones, you have a positive direction, negative direction. Just take the positive direction. And the point is that a hyperbolic affine sphere will kind of look like this. Kind of these floppy objects that all kind of look like one sheet of the hyperboloid. Okay? And the way Mike phrased this was that he said that these hyperbolic affine spheres are graphs over this convex set. But if you think about what a graph over a convex set is, that's asymptotic to this cone over here. Okay? So they all look like this. So in particular, in this example of one sheet of the two sheet of hyperboloid, this convex set is a nice round circle. And in fact, if you studied hyperbolic geometry, then you recognize this model. This is just a Klein model of H2, okay, where geodesics are straight lines in this disk model. So you've seen this interpretation of hyperbolic affine spheres before. Okay, and now to connect it, why do I mention the result by Hitchin, Choi, Goldman, and so on? Well, it turns out that this convex set comes from the developed image of the convex real projective structure. Okay, remember I had this, charts to RP2, transition maps or Mobius transformations. I can continue to unfurl these images until I develop the image in RP2. And that'll be a proper convex set. And that's the convex set I take to build my hyperbolic affine sphere. So in this way, this connects, we start from Hitchin representations, we get convex real projective structures, you get a convex set, and using this convex set, I could build my hyperbolic affine sphere by taking its cone, and then the Cheng-Yao result says that there's a unique hyperbolic affine sphere asymptotic to it. Okay, a little bit slower than I would have liked, but now let's try to, so I covered the first part about SL3R Hitchin representations. Now I need to talk about Blaschke metrics. And this is coming from the hyperbolic affine spheres. Now, of course, Mike gave a different interpretation of, equivalent, but perspective of Blaschke metrics. But what I can do is, if I'm in R3, I have the standard flat connection. So let's say sigma is is a hyperbolic affine sphere. Well, if I look at the second fundamental form, so let's say I take this trivial flat connection, well, I have a connection induced on the surface here, and I have a second fundamental form. So here, with respect to my affine normal. And Mike pointed out that this here is positive definite when I have a hyperbolic affine sphere. So it's positive definite, bilinear, so that's a Ramanujan metric. So this is a Ramanujan metric on the surface called the Blaschke metric. Okay, so okay, good. And this Blaschke metric, well, okay, so here, this nobla here, this induced connection, this nobla here is called the Blaschke connection. That's one connection. I could form a second connection because I have Riemannian metric here. I can take the Levi-Civita connection. So here the Levi-Civita connection of the Blaschke metric. Okay. And it turns out these two connections are not always the same. In fact, they're seldomly the same. In fact, there's a precise instance when they coincide, but usually they are not the same. So if I have two connections, what can I do? I can subtract them, and what I get is an endomorphism valued one form. Okay, so that means you hand me a vector, then this gives me an endomorphism on the tangent bundle. But then I can pair this with the metric. So if I raise or lower indices paired with the metric, H, now I get a, maybe say cubic tensor for now. So what do I mean by this? You hand me three tangent vectors, out comes a real number, right? Because I could take I could take one of the tangent vectors to get my endomorphism valued one form. Then the endomorphism will act on the second tangent vector, spitting out another tangent vector. And I take my third tangent vector to pair it up with this Riemannian metric to get a real number. Okay? And it turns out that this tensor is the real part of maybe twice the real part of a holomorphic cubic differential. So the so-called PIC differential that Mike mentioned. So what we get is that, I don't write this down, we get a holomorphic cubic differential. Q called the PIC differential. Okay, now you might say, well, what are you talking about? Holomorphic, I need a Riemann surface. Well, as Mike mentioned, you have this Blaschke metric here. This gives you a conformal class of metrics and hence a complex structure on the surface. So it's holomorphic with respect to that. And then we have these famous integrability equations for the affine sphere, which I will rewrite again. If I choose some conformal background metric on my surface, then I get this following minus 4e to the minus 4u. And here you see this is my cubic differential here, and I have a curvature. And this is G is a conformal background metric. So, okay, so now this is definitely something new. I mean, we've seen this equation before, but Mike was working on C, right? So this curvature term vanished. So now I'm working on a closed surface, right? So if I had to pick any metric, I would just pick the hyperbolic metric to make my life easier, right? So now this term becomes a -2. Okay, but you're welcome to choose any background metric, okay? But you need to make choose background metric. And strictly speaking, I suppress some details here, but to make sense of norm of the cubic differential, this with respect to a metric. So that's the same one here. And you can see that there's some similarities with the Bachner equation that we saw for harmonic maps between a Riemann surface and hyperbolic 2 space, and that's no coincidence. And this is kind of the nice situation, which we should see in about a few minutes before I end, how these relate to Higgs bundles. I mean, tie this in with Franz's lecture. I mean, this is one aspect of the Hitchin equations. So if you write down these SL3R Higgs bundles, if you write down Hitchin self-duality equations and you work a little bit, then you get this scalar equation here. So these are the Hitchin equations for SL3R. And these are the nice sign combinations. So tomorrow, when I give this lecture about minimal surfaces without Higgs bundles, then we flip the sign. You can see that this makes our life a lot harder. Okay, so let me just try to wrap up. So putting this all together, this is a very nice theorem due to the Labrie and Lofton independently. But now there's a homeomorphism from the hitching component, the SL3R hitching component, remember these representations, and now we get not just Teichmüller space, right? So we saw before representations into PSL2R corresponded to elements of Teichmüller space, but now when we upgrade to SL3R, it's not just Teichmüller space, but it's this here is the bundle of holomorphic cubic differentials over Teichmüller space. Okay, so let me draw a picture. And we've seen this. Why? I mean, how do I get my Riemann surface, my element of Teichmüller space? That's the conformal structure of the Blaschke metric. And how do I get my holomorphic cubic differential? That's just the Q that occurs from this difference of the Blaschke connection and the Levi-Civita connection. So here's a picture. Here's Teichmüller space. You pick your favorite Riemann surface, and the fiber is the vector space of holomorphic cubic differential. So this is my script C of S, not to be confused with the first script of C of S that occurred at the beginning of this hour. Okay, so there's the correspondence there. Okay, so now let me try to tie this with Higgs bundles, because so we've seen already, at a very high level in this conference, these parabolic Higgs bundles that Pedit talked about. But for today, we deal with closed surfaces, so there's no parabolic weights. But let me at least define a Higgs bundle on a Riemann surface. So these have a few pieces of data. The first thing I need is a holomorphic vector bundle, holomorphic rank and vector bundle. Okay, so of course, this is why I need a Riemann surface. And then I have a Higgs field that we kind of saw in Franz's lecture. Okay, so a Higgs field here, and this here should be, this is an endomorphism valued, and E, right, the same E valued 1 form. Okay? And a holomorphic. Okay, so a fancy way to write this is that it's a holomorphic section of the bundle end E tensor K. Okay, so kind of the corresponding Higgs bundles that we have here, which unfortunately I don't have too much time to explain how we derive this, but what we get here is the following. So for SL3R, and now I need to peek at my notes because I always mess this up. And then I get laughed at by experts in the audience. I still mess this up even with the notes, but okay. So what we do for the bundle, it'll be, okay, because you see that I have SL3R, okay? So I can maybe complexify and have maybe GL3C. So it should be a rank 3 holomorphic vector bundle. So the bundle I have will be a canonical bundle dual. I take the trivial bundle, and then I have the canonical bundle. Okay, that's a perfectly fine holomorphic vector bundle. And my Higgs field will look like this. Okay, if you work out the tensor type, you can see that this here is an honest 1 because it goes from, let's see, it goes from, oh, of course I messed up my linear algebra now. It goes from O to K inverse tensor K, right? So that goes from O to O. So this is an honest real number, 1. Okay. And likewise, this here goes from K to O tensor K. So that's going from K to K. So this here is an honest 1. And over down here, you'll notice that I'm going from K inverse to K tensor K. That's going from K inverse to K squared. That's a K cubed. And that's exactly a holomorphic cubic differential. And in fact, using this correspondence, this Q is exactly the same Q as that pick form that we saw earlier. Okay, so you could encode all this data in terms of the Riemann surface we pick is the conformal structure coming from the Blaschke metric. I write down this rank 3 vector bundle. I have this Higgs field, and I have the single Q. And if I write down the Hitchin equations, right? So we saw this earlier, namely, okay, maybe I don't write this. So the curvature of the Chern connection, which I don't explain now, plus some commutator term, then if I write this out, then I get exactly the scalar equation here. Okay, so that's, let's see. Okay, so now one last thing then. So let's finally get to kind of the minimal surfaces part of this. Well, because when I have a Higgs bundle, I could solve the Higgs equations. This requires a Hermitian metric on my bundle. And you can see that the Hermitian metric is a Hermitian metric on this rank 3 bundle here. Okay, but in fact, you could show that in SL3R, this is actually Ramanujan. And on K here, the metric on K is the Blaschke metric. Okay, and of course, here, this will be the Blaschke metric dual. And then on here, on O, it will be just the trivial metric. And the trivial metric I pick will be the metric which assigns to the affine normal, as Mike mentioned, length 1. And you can see that this is a metric on my rank 3 bundle. In fact, since it's a Ramanujan metric, this is a metric on R3. And so the point is that when you have one of these Higgs bundles, what you get is a going from these Higgs bundles, what you get is a harmonic map from the universal cover of my Riemann surface to the symmetric space SL3R mod SL3. These are metrics. And the metric is very, okay, so there's a lot of metrics floating around, right? So this is the space of these metrics on R3. And the actual point that you pick, so if you start with your Riemann surface, you pick a point, you map this over by this harmonic map. That harmonic map, the image of a point is exactly that metric that I have on that rank 3 bundle here. Namely, on the tangent space, it's the Blaschke metric, and in the affine normal direction, it's length 1. And I've declared those to be perpendicular. Okay, so that's the actual explicit harmonic map here. Now you can see that actually this map, when I choose Higgs bundles of those form, it's actually a conformal harmonic map. And you can actually show that it's an immersion. So these are minimal surfaces in the S. No. You have to choose. So I've chosen my Riemann. No, that's, Parker asked questions that he already knows, but that's good because I'm hiding some things and he's trying to keep me honest. So at some point, remember, we had to choose a Riemann surface to make sense of a Higgs bundle. And the Riemann surface I picked was the Blaschke metric, formal structure coming from the Blaschke metric. And if I do that, then the map will be conformal. But if you're sloppy and just choose any Riemann surface, then chances are it will not be, in fact, it will not be conformal. Yes? Yeah, oh, Parker, again, oh, this is, I pay you afterwards. Remember, the conformality condition is that you have a Hopf differential, quadratic differential. But if you look at this Higgs field here, there should be a place where there's a quadratic differential, where it goes from K inverse to O tensor K. That's a K squared. But you'll notice in that slot I have a 0. So in fact, you can work out that where that slot ought to be. That's the Hopf differential, and it's 0 in this case, so it's actually conformal. Sorry. Okay. Maybe. Does that answer your question, Parker, or is that good enough? Do I pass? Okay. So now I have these minimal immersions in the SL3R symmetric space, and let me just go over time maybe by 1 or 2 minutes. Okay, so I've given this lecture. Okay, so now let's at least kind of say something about these minimal surfaces. So I've already described, what the points on this minimal surface are, right? The individual points on these minimal surfaces, right? The minimal surface lives in this symmetric space. The actual points are these metrics where the tangent plane is Blaschke metric and the perpendicular is the affine normal of length 1. So we could ask qualitative questions about these minimal surfaces, in particular the asymptotics of it. So what happens when you degenerate this minimal surface? Much in the very same sense that at the beginning of the hour, we looked at degeneration of these hyperbolic metrics. And one way that you could study this degeneration is to look at the degeneration of the Blaschke metric. Remember, you have this PDE here? Well, the Blaschke metric turns out just to be this conformal factor hey, I would take the background metric, be the hyperbolic metric. Then this conformal factor is the solution to this PDE here. I get a function u, and that's the conformal factor so that I can go from the hyperbolic metric to the Blaschke metric. And if I, had a little bit more time, you could see that, for instance, when q is equal to 0, then u is equal to 0, and that's exactly the Blaschke metric, the hyperbolic metric. Okay? But when q is not 0, then you get something that's not equal to a hyperbolic metric. These are the Blaschke metrics. And in kind of just one line, there's an old theorem due to myself and Andrea that classified the limits of these Blaschke metrics. And I have this schematic here, which I keep. So the point is that if I kind of stay in this, I mean, there's a couple ways to generate in this, Hitching component, right? So this is the picture of the Hitching component due to Lowry and Lofton. So I can kind of go up this way. And if I go up this way, the Blaschke metric starts to flatten out. You might kind of give this heuristic where you have these triangles. So the metric starts to look flat. Whereas if you went this way, you would get a measured lamination. Okay, that's no surprise because if I stayed here on Teichmüller space, the Blaschke metric is the hyperbolic metric. So I get these measured laminations. Kind of the new thing that Andrea and I did a while ago is that if you go in these directions where you're neither staying in a compact set in Teichmüller space, nor are you bounded distance in some sense to Teichmüller space, you get these mixed structures where on the topological surface, part of it is a flat metric, and part of it is a measured lamination that I drew earlier. So it's a part Ramanujan metric, singular, and a part measured lamination, which is not a metric. So these are kind of the hybrid objects. So the point is that when you do this, these are the limits. And in some sense, that's the limit of the point on the minimal surface. Now you can actually, in the last 30 seconds, you can ask about the induced metric on the minimal surface. That's a lot of metrics there, right? Because this here is a space of metrics. The individual points are images of this minimal immersion, right? And this minimal surface itself carries a metric. And you can ask, what does that metric look like? And it turns out that when you start to degenerate, that metric starts to look more and more like the Blaschke metric. So the point is that once you understand the asymptotics of the Blaschke metric, you actually have understood the asymptotics of the induced metric on the minimal surface. So, and it turns out that it's exactly the same schematic here. So I'm over time, so I should stop here. Thank you so much for your attention.
Thanks, Charles. Right. Thank you. So Franz gave these very nice Yang-Mills Higgs equations.
Yes, yes.
I was wondering if you could say a word about, in this context, we have this holomorphic vector bundle here and this Higgs field, this holomorphic object. So how can we see some nice partial differential equations in this context? What are these equations for the metric H?
Well, okay, so if you write down the Hitching equations for this bundle, then out comes this equation here, the scalar equation here.
So in this special case, but perhaps maybe form a more general perspective, can we see some equations in this context that are very similar to the equations that Franz wrote down?
I don't know what you're getting. I mean, maybe I don't understand what you're getting at. I mean,
like the equations for a flat connection on this.
I see. I see. Well, okay. Right. Okay. Right. So what I think what Parker's getting at is that he's asking flatness of what? Is that what you're asking? Okay. So right. So this is kind of things I did not say that I maybe should have said. So there's this nice non-abelian Hodge correspondence that takes me from Higgs bundles back to flat connections. Remember, I have a holomorphic bundle here, right? So I could forget about the holomorphic structure, and then I just have a regular rank 3 vector bundle. And it turns out this is a degree 0 bundle. That's maybe something I should have mentioned here. You can see in this example, this has degree 0, right? So it's a flat vector bundle, so it actually admits a flat connection. And there's a very specific, a hands-on way to actually cook up this flat connection coming from the data of the Higgs bundle. So what you do is you take the Chern connection. So you choose an auxiliary Hermitian metric. You already have a complex structure here. So this gives you a Chern connection. So it's a unique connection that's unitary with respect to your Hermitian metric and whose 0, 1 part is the of this connection is the holomorphic structure on E, and then you can add it with the Higgs field and its adjoint with respect to the Hermitian metric. Okay? This is just formal. I'm just writing, you choose a Hermitian metric, I could write this connection down. And it turns out this is kind of the deep theory of the non-abelian Hodge correspondence in one direction to the Corlett and Donaldson, in the other direction to Hitchin and Simpson, is that I could find a best metric that makes this metric flat. So let me just write this metric as D here, or maybe just Nobla here. And the flatness of this is exactly the zero curvature equations that we saw from Franz. Okay, so and when you write down flatness of this using this, then out comes that equation there. Okay, so that's the so if you're sloppy and you just choose any old Hermitian metric, you won't be able to get that this is flat here. And this Hermitian metric is exactly the Hermitian metric I was talking about on this bundle, where it's Blaschke metric, trivial metric, and Blaschke metric.
Can you maybe write down what shape the Hermitian metric H will take?
It's diagonal, but I don't say much more than that. So it really is exactly what I said. It's Blaschke metric here, trivial connection, like 1 here, Blaschke dual here. Yeah. But you can play around with it because you have strong symmetry properties with your Higgs field. Is what's called a cyclic Higgs field, and you can work out that it has to be Hermitian using the uniqueness property too.
Could you just remind me how to go back from the surface?
Oh, that's a good question. No, thank you for that question. Okay. Yes. So if I have this minimal immersion, right, then this is the same thing as having a. Okay, maybe there's 2 ways to answer this. Okay. So let me see if So if you have this minimal immersion, then you at least know where the you know what the image is, right? So you know what points in the SL3R symmetric space you're at. And what you get is that if you know what the metric is, then you can figure out, you can find the Blaschke metric from this. Once you have the Blaschke metric, then you know the conformal type, so you know your Riemann surface. And it's a slight lie, you can also recover Q up to some factor. But once you have Riemann surface and Q, then you have your Higgs bundle.
Just a quick basic question, sir. So you had a theorem of Cheng and Yao,
yes,
where you are able to, step by step, Hitchin representation was ultimately related to the cone.
Yep.
So where did that connect in after that? Like you.
Okay. I see. Okay. So you're happy from all the way from Hitchin component to Cheng Yao. Okay. Once you have Cheng Yao, so remember Hitchin representations gives you these convex real projective structures, which gives you the convex set, which gives you a hyperbolic affine sphere. When you have your hyperbolic affine sphere, this is living in R3. Then you could decompose the flat connection into Levi-Civita, a Blaschke connection and Blaschke metric. And then the Blaschke metric, yeah, exactly. Then that gives you the Higgs bundle then. That gives you both the Riemann surface, the holomorphic cubic differential, and then you can write down this Higgs bundle.
And just one more question with this. Here you got this cubic differential, right? From this. So when you're going back to the Riemann surface, you are trying to get a pullback metric on it, or like how is Z related to that Q?
Sorry. So you're saying, sorry, this equation?
You got some cubic, the differential here?
Here, yep.
Yeah, from here you got this Q where you had this cubic differential.
Yes.
So how is it related to the metric? Like G, we are putting it on the Riemann surface, right? So is it like we can, how is this Q connected to G? Like what choice of G?
G or H?
From H,
yeah, well, yes, yeah, from this I get Q, right? But yes, that's also. Oh, G is just any conformal background metric. So H already determines a Riemann surface. So in kind of the wrong direction, I can choose a background metric that's compatible with H, right? So I mean, in some, yeah. So you want to make sure that you choose you can choose anything you want, but you just can't choose it outside of the conformal class.